And today we're really pleased to have David Gross from the University of Cologne. He's an expert on the Clifford group and also on quantum information. And he's going to tell us about representations of the Clifford group with applications in quantum information. So David, it's to you.
Okay, yeah, thank you for the kind introduction, and thanks to Arthur and the team for inviting me. There is again some feedback. I think Mr. Lizong Peng, I think it comes from your computer, I just saw. So maybe you want to mute your microphone. Yeah. Okay, let me get my screen share. So I will be giving this presentation in wearing the uniform of Corona times, where I wear a white shirt, but I also have shorts, and I wear no shoes. I hope that's fine, because I will try to like hide behind my desk most of the time so that it looks respectable what I'm doing here. Okay, right. So that's the outline of my talk. This is a mathematical physics seminar, and I'm going to give a quantum information talk. Now, there's been many quantum information talks in the series, but I think it's still true that it's a very heterogeneous audience, and yeah, I think I will I spent a significant amount of my time, let's say the first 20 minutes, just repeating elementary stuff, just in order to like introduce the jargon of quantum information here and explain what I mean by this Clifford group. Let me, I have a laser tool, maybe you can see it. Yeah, I will just explain what I mean by that for the first 20 minutes. All going to be elementary, just to like find a common language. Right, so then I will go through a number of applications, yeah, either representation theory, and then I will go through a number of applications. There's a new paper from a few weeks ago that I was invited to present. It's, the title is here, it has a funky name, Quantum Homeopathy. And I was asked to talk about this, but actually I will spend the majority of my time explaining the wider research program for which this is an application. And if there is time, and if there's time, I can, I have some spare slides on even more representation theory if people would like to hear about this and there's time. Good, okay, so let me first start with my introductory section where I will say nothing new at all. And my aim is largely to set up a dictionary between terms that will be familiar to most people in the audience. Yeah, and these are elementary concepts from the theory of continuous variable many-body quantum mechanics on the one hand side, and on the other hand, I will introduce analogues of this, which are defined for discrete variables, which are more commonly considered in quantum information theory. Yeah, so the increase of my dictionary is I will introduce what a stabilizer state is. This will turn out to be some discrete analog of a Gaussian state. I will talk about generalized symmetries, which are given, for example, by generalized Pauli operators or Weyl operators, which are discrete analogs of the Weyl operators in continuous variables, which again are exponentiated versions of the, or like an incarnation of the CCR algebra. I will talk about then the Clifford group in this sense, which is kind of a discrete version of canonical transformations. And I will also mention stabilizer codes, which don't really have a nice analog on the left-hand side. Yeah, and these notions are extremely important in quantum information theory. You all know this for the left-hand side, where we have this quote by Michael Peskin, who said that physics is that subset of human experience which can be reduced to coupled harmonic oscillators. And of course, yeah, all these Gaussian states, what they describe are ground states of harmonic oscillators like systems. And if I may, give you the quantum information analog here, quantum information is that subset of physics which can be reduced to Clifford actions on stabilizers. So this right-hand side column is really fundamental to quantum information theory. Good. All right. Okay. So I will just to introduce a common language, I will just recapitulate elementary concepts. So let's start looking at a Hilbert space of n continuous degrees of freedom, L2 of Rn. Yeah. Then a particular rich but simple set of wave functions there are Gaussian wave functions, which are described by some matrix C, the quadratic part, and some vector B, and then the wave function at a point x in space is given by this complex exponential with a quadratic exponent. Yeah, they are important, of course, because they form the ground states of Hamiltonians, which are quadratic in position and momentum operators, so the generalization of the harmonic oscillator. And they can be characterized concisely and most conveniently using the 2n² values of the covariance matrix, which sometimes it's symmetrized, is the matrix containing these expectation values. More important, actually, or like very important also in this context, are the symmetries of the set of Gaussian states. So let's look at the unitaries that map Gaussians to Gaussians. The most fundamental one are the Weyl operators, which shift the wave function in position and in momentum space. So we can write them by exponentiating position and momentum operators that fulfill the CCR. And the group law for which the CCR is a Lie algebra is then given as follows. So if I compose two of these shifts, then I get basically something that's almost abelian, yeah? So the indices, the shifts add up, but there's a twist, quite literally a twist, yeah, some phase, and the phase depends on a symplectic inner product between these arguments here. So somehow symplectic geometry, of course, coming from the classical phase space is seeping into quantum mechanics via that connection. A bit more interesting are the canonic transformations, which are unitaries that act on the set of Weyl operators and by conjugation and thus preserve the group law. And because the group law involves a symplectic form, it is plausible and indeed true that these transformations here, they are parameterized by symplectic maps on phase space. Yeah? So for every symplectic map on phase space, one can find such a unitary fulfilling that relation. And this has been rediscovered many times and plays an important role in many different fields. So that's why this has many different names. Some people call this the metaplectic representation of the symplectic group, or the oscillator representation, or bosonic Bogolyubov transformations, or canonic transformations. The list goes on. Yeah, these are all the same objects. Right, there's a final slide on recapitulating Gaussian quantum mechanics. Yeah, the Gaussian wave functions form an orbit under this action of the affine symplectic group, yeah, where the Weyl operators act by translation and the symplectic group acts linearly. Okay, good. So you all knew that. Now let's switch over to quantum information and introduce the discrete analog that this talk will be about. Good. So in quantum information theory, our Hilbert spaces tend to be finite dimensional. So we look at, like, let's say, an n-fold tensor product of CD, some finite number. Yeah, we will usually take this maybe to be a prime number. There's a disclaimer here that everything I say on my slides is true up to some technicalities in even characteristics. So you are free to choose like these elementary dimensions in like, yeah, any value you want. But if you choose 2, then some of my statements need to be slightly modified. But I will not put these technicalities onto the slide, so they are on the papers. All right. Okay. So now we need to introduce a discrete analog of Gaussian states, and these turn out to be stabilizer states. And our first attempt could be to be a bit naive and to just write out a wave function that depends on a discrete set of indices here. I mean, this Hilbert space can be realized as the Hilbert space of functions on zd to the n. Yeah, so the integers mod d and n copies of that. And if I get such an integer vector as an argument to the wave function, I can just evaluate, naively write down an exponent and put in a quadratic form into the exponent, and I could call this my discrete analog of Gaussian states. And so this turns out to be a very fruitful definition. So the set of stabilizer states includes all of these, but there will be a bit more. And to explain to you what we need to add to get the full theory, I will talk again about the symmetries. Okay, so let's talk about the symmetries of the set of stabilizer states. So the maps that map stabilizer states to stabilizer states. And the first thing that we do is we introduce a discretized version of the Weyl operators. Yeah, and so we have these generalized shifts that shift in position space. What they do now, if we are working in a finite setting, is that the shift becomes cyclic. Yeah, so we wrap around after we hit D. Yeah, and then the Fourier transform of that is a diagonal operator, which acts as a multiplication operator, of course, by a phase. Yeah, and then we can define the discrete analogues of these Weyl operators depending on integer arguments p and q as momentum space shift by p, momenta, and position space shift by q. And now we can look at the theory, and it turns out the theory here really unfolds in a completely analogous way. The group law is again almost abelian. Again, there is a phase. Again, this phase depends on some symplectic form. And again, we have the symplectic group being represented here as the group of automorphisms of these Weyl operators. So for every discrete symplectic map, right? So this is now an integer matrix that preserves the standard symplectic form on this space. We get a unitary that acts on the set of Weyl operator in exactly the same way as we know from the continuous variable case. And so the group generated by these symplectic matrices, and sometimes also by these Weyl shifts, if I include them, this is what we call the Clifford group in quantum information theory. Yeah, so that is the object I'm talking about. It's not usually presented this way in quantum information literature. So if you open, I don't know, like Nielsen and Schwang, then this group is very important. It's a central ingredient to quantum information theory, but they will not even mention the word symplectic, but instead they will write out a set of generators for this group, directly write out the generators as unitary matrices. But you can make a connection to the symplectic picture. Good. Now I can, with this preparation, I can give you the definition of what stabilizer states are. That is a bit more general than these Gaussian that we've seen before. Okay, so let's start with the group law of the Weyl operators. Then we can see here that this phase vanishes if the symplectic form between the two arguments vanishes. So Weyl operators commute if and only if they correspond to vectors with a vanishing symplectic form. And now let's make a few definitions. Yeah, so a subspace, that should be like ZD. Yeah, a subspace of this finite symplectic vector space is called isotropic if the symplectic form vanishes on the subspace M. If I have an isotropic subspace, then the Weyl operators corresponding to the elements in this subspace, they are abelian by this argument above. And they are called in quantum information a stabilizer group. Because they all commute, they have a joint set of eigenvectors, and the joint +1 eigenspace of these Weyl operators, that is called a stabilizer code. Yeah? So we have a way to turn an object from a symplectic geometry, namely an isotropic subspace, into a subspace of a Hilbert space. Yeah? So it's something discrete, a discrete geometry will be mapped onto the Hilbert space geometry. If the dimension of this isotropic subspace is n, which is to say it's Lagrangian, so it's the biggest dimension an isotropic subspace can have, then this subspace, this joint +1 eigenspace turns out to be one-dimensional, and is then called not a stabilizer code, but a stabilizer state, right? And now the results to connect with what I said before is that again, we have that stabilizer states are one orbit under the affine symplectic group, but now everything is discrete. Yeah, and in fact, all Gaussians arise this way. Yeah, a few more vectors arise this way, and I've given you an example here, but actually, I think I will not talk about this because the details are a bit unimportant here. Yeah, please ask me later if you want to know more. Good. So now we have a way of turning like a discrete symplectic geometry into an interesting group acting on a finite dimensional Hilbert space and an interesting set of states that they act on. I said before, quantum information is full of applications of that. Many constructions, many constructions in quantum information employed. The most important application of stabilizer codes is quantum fault tolerance. Yeah, I cannot explain this here at all, but maybe just one slide to motivate the importance of this construction. Of course, in quantum computers, if you would like to implement them, then the biggest challenge to overcome is noise. Yeah, so if I start in some simple state and apply unitary gates to perform a computation, and then I want to read out the result, what will happen more likely than not is that, some interaction will take place with the system that defines the qubits during the time of the calculation, and this will screw up the result. So in order to combat this, we need to use ideas from quantum fault tolerance. And the basic construction is that every qubit will become a logical qubit that will be embedded into many physical qubits. Yeah, so this is like depicted here. So like every logical qubit in the upper line will be encoded, and there will be a we choose a two-dimensional subspace of many qubits, and then all the operations will be performed on this encoded state. And if we choose the encoding wisely, sometimes it so happens that if some error will affect a physical qubit during the calculation, then during error detection and correction stages I have in the middle, I can identify this error and correct for it. Yeah. So okay. So of course I have would be another talk to explain how that works in details, but the important fact here is that all known such encodings are stabilizer codes, and all robust gates that can be realized this way fault tolerantly are Clifford gates, where when I say all, I mean virtually all. There's like a tiny subset of the field that looks at non-stabilizer codes, but they don't play a practical role. Yeah, so yeah, the most important selling point of quantum information is the prospect of building a quantum computer, and there the most important problem is quantum fault tolerance, and again, these stabilizer codes are what drives that field, so it's really important. Okay, good. I'm basically done. I have stabilizer states 3 of 2. I will have one more slide because this is the mathematical picture project, and I haven't had any pictures yet. So let me show you some pictures. So, I made a very close connection between like the continuous variable Gaussians and these discrete Gaussians. So at the level of wave functions, the continuous theory and the discrete theory, they seem very similar. But the way they are specified is very different. On the one hand, we have covariance matrices, and on the other hand, we have these stabilizer groups. They are these isotropic subspaces. So how do they fit together? And the way they fit together can be seen here. Yeah. So if we start with the Gaussian, and now imagine we will squeeze the system by reducing uncertainty along one axis and increasing uncertainty along the other axis. Then if we squeeze more and more and more, we end up in the limit with a Gaussian that is translationally invariant along one direction. And so the covariance matrix, it will have a kernel. It will the uncertainty along this direction will vanish, and it will tend to infinity along the orthogonal direction where we have translational invariance. And so in that sense, one can sometimes describe infinitely squeezed Gaussian states can be described in terms of the directions along which they are invariant. And so that is how one can think about stabilizer states. So stabilizer states really are the analog of infinitely squeezed Gaussian states. Yeah, and that's why we describe them in terms of their invariances and not in terms of their covariant matrices. Good. Right. Yeah, that's what I just said. Okay, so that concludes my introduction. We've set up this dictionary between Gaussian quantum mechanics and stabilizer states in the Clifford group. And if I had to summarize again why these are so important, then I would say that these structures, these unitaries, these state vectors, they are rich enough to capture interesting phenomena, but they are well behaved enough to still allow for an explicit analysis. And so that's why they're so important in the two fields. Good. So let's talk a bit about representation theory of the Clifford group. And you can see I will have more pictures here. This will be a pictorial language. It's going to be very simple, but important, actually. So here's my central question for this talk, and let me give you the code to this pictorial language. Right. So I will always look at a collection of n systems, and this could be n continuous variable degrees of freedom. So every dot could correspond to the Hilbert space L2 of R in the continuous theory, but a dot can also sometimes correspond to a finite single particle Hilbert space, which would then be CD. Yeah, and now I have n of those. And next, what I do is I take t copies of that system. Yeah, so now I have a two-dimensional array of tensor products. Yeah, so if you want, I have C tensor D to the N to the T. And because these like two levels of tensor products will be very important to keep apart, it's a very good idea to have this graphical notation where always one will be denoted by a horizontal line and the other one, T, by a vertical line. Okay, so now these blocks, these dots in this way, they define a big tensor product Hilbert space. And what I want to do now is the following. I choose a unitary U, which will usually be a Clifford, an N system Clifford unitary. So we have these, this blue blob means U will act on these N systems, and it will identically act on each of these T copies. And now the question I would like to solve, what I would like to understand is, I want to understand the representation theory of the T-fold tensor powers U to the tensor T of Clifford unitaries. Yeah, it's a diagonal representation, T's tensor power. What can we say about the representation theory? And there are two follow-up questions that you might have to me. And one is, why should I care about this? And the other is, what do I mean by to understand? Yeah, what is the precise goal? So let's look at these two questions in turn. So first, why should anybody care about this question? Right, okay, so this slide is, the intention of the slide is proof by intimidation. I will not actually go through this list of applications. I just want to say that, if you're working quantum information theory, because the Clifford group is such a central tool, there is many protocols, many problems that if I want to understand their performance, question about their performance can be asked in terms of representation-theoretic data of the Clifford group. And so there's really many. What the slide would like to tell you is that I will ask you for maybe the benefit of the doubt. Maybe please believe me that these questions have many applications, and I will only present a few of them. Yeah, but it's a subset of what they can be used for. Okay, so let's pick a few applications for problems where this question comes up. And the first one is maybe a bit, it's a toy application. It's maybe not obvious that it's very exciting, but it's very simple, and it guided our investigation a lot. So I think it's good to start with that. And it goes in quantum information by the name of stabilizer testing, but I want to call it guess whether Gauss, right? And here's the problem, the guess whether Gauss problem. So let's assume somebody gives me T copies of some unknown state, psi. Yeah? So somebody prepares a pure state psi in the lab, and they prepare, in fact, T copies, and they hand these T copies to me. And now they want me to decide whether psi was a stabilizer state or whether psi is far away from the set of stabilizer states. Yeah, so that's the game we want to play, and I have to guess correctly. And this is a fact. This was posed as an open problem a few years ago in a theory called quantum property testing, and there's some context, but I will leave out the context. Namely, the question was, is it possible to win this game with a construction and probabilities of success and number of copies T, which are dimension independent? Yeah, so that makes it difficult because, if it's dimension independent, I could just set T to be, I don't know, 2 to the n, yeah, and exponentially big in the number of systems. I could perform like a complete set of measurements on psi, just reconstruct psi, and then I have the complete information in my classical computer, and I can just check, is it a stabilizer state or not? So that's obviously possible, but it's also very boring and also, practically impossible because it takes exponential effort. So the question is, can you do it in a dimension independent way? All right, so let's make a simple ansatz which tells us how representation theory enters this game, and it will lead to some interesting applications. Okay, so let's try to decide whether we can win this game. So let's fix some T, and then a natural quantum measurement I could do on my T copies would be the following. I take P step to be the projection operator that projects onto the span of the T's tensor power of all stabilizer states. Yeah, so if I vary over psi over all stabilizer states, then their T's power will span some subspace, and P step is the projection operator, so that is one of my two measurement outcomes. Yeah, and if I measure p step, then I will say yes, it was a stabilizer state, and then I complete this measurement by taking the identity minus p step, so the projection onto the ortho complement of the span of all stabilizer states as my alternative outcome. So that's a good answer, and let's see what we can say about it. So the first thing to note is that the analysis will probably be representation theoretic, because the set of stabilizer states is an orbit under the Clifford group. That means, of course, also that the Tth tensor powers form an orbit under the Tth tensor power of the Clifford group. Yeah, so the thing lies in the commutant of this group. And so we can like now use some representation theory, and let's see whether it works. And the first results will all be negative. It doesn't work first. Yeah, so first we can try t equal to 1. Yeah, it doesn't work because it turns out that if you only have one copy, then the space spanned by all stabilizer states is in fact, yeah, equal to the space, to the entire Hilbert space. So no non-trivial testing is going on. Yeah, for t equal 2, it's still the case. Then p step is the projection onto the totally symmetric space of 2 copies. So again, p step does not actually depend on the set of on the stabilizerness of the input. It will just accept any input that is a tensor power. Yeah. So t equal to 2 also doesn't work. This has been long known for a long time, since 2002 at least, the oldest reference I could find. T equal to 3 also doesn't work. Yeah, this took until 2015 to find out. T equal 4 also doesn't work for exactly the same reason, because even if we go to 4th tensor powers, it is still the case that, yeah, the 4th tensor powers of the stabilizer states just span the entire totally symmetric subspace. T equal to 5 also doesn't work. Yeah, so and you can see the people have more and more interest in this question. The time gaps are getting shorter. And I will tell you later in this talk that an optimal solution can be found for t equal to 6. But before I tell you that, I will first try to take all these negative results and turn it into something positive. Yeah, so I believe there is this American proverb that you can turn lemon into lemonade, and let's try to do this and turn all these negative results into something constructive to say about quantum computers. Okay, so that's the second application of why I want to present to you of why this question is interesting. Right, so first, let me state some facts. There is what is called the Gottesman-Nil theorem, which states that if you have Clifford operations acting on stabilizer states, then this, whatever they do, can be efficiently simulated on a classical computer. That is not very surprising because you have this concise description in terms of stabilizer groups. So you don't actually need to track the time evolution in the exponentially big Hilbert space, but you can just stay in this group theoretic description. And so that is easy to do on a classical computer. And then there is the next realization, namely that if one takes Clifford unitaries and stabilizer inputs and some non-stabilizer input, then this is in fact universal for quantum computation. So yeah, if just a small number of the inputs are non-stabilizer, then the circuit can efficiently simulate any quantum computation. And because we believe that quantum computers are more powerful than classical computers, there's no way to classically track what happens in such a circuit. And this is a very attractive model in quantum information because somehow like all the super classical part, all the potential power of the quantum computation is contained in this particular input state. So it's nicely concentrated, which is why it's called the magic state model of quantum computation, where these inputs here are called the magic states. Good. And now an important question is, if I want to, let's say I want to anyway simulate on my classical computer this quantum computation. I know it will take exponential time. And if I do it naively, it will take time that is exponential in the total dimension of the Hilbert space. But if I'm very smart, maybe I have a chance to come up with an algorithm that is exponential only in the number of non-Clifford inputs. And this is indeed true. And in fact, even the constant here, in front of the number of non-Clifford resources, even that constant tends to be, can be shown to be smaller than 1. So very effective, very efficient classical simulation algorithms can be proposed. Let me I mean, still exponential, but they can push, the classical simulations can be pushed much further than you would naively suggest. So let me explain to you how that works. The idea is very simple. So yeah, there's this idea of stabilizer rank that has been proposed a few years ago in this paper, and it's at the moment one of the best classical simulation algorithms we have for quantum computers. And so the idea is this: we take this non-stabilizer resource, and we write it as a superposition of stabilizer states. Yeah, that is always possible. The set of stabilizer states, they generate the entire Hilbert space, so you can always find such coefficients. And if you are very lucky, then the number of coefficients you need is not too much, not too many. And if it's not too many, what you then do, if you want to simulate the entire calculation, yeah, you simulate the circuit summand by summand. Yeah, every summand is a stabilizer input, so we can use Gottes-Manil to simulate it. Yeah, and then I do it for all these summands individually, and then I combine the results. Right, so if I get a small stabilizer rank for these inputs, then I have a relatively good simulation algorithm. Yeah, and in fact, I think I think in many cases it's the best currently known classical simulation algorithms for quantum computers. Right, but now the question has just been shifted. Now the question is, can one bound the stabilizer rank? Can one show that, you know, these input states can be written often as a superposition of not too many stabilizers? Yeah, and this is where we can now turn the lemon to lemonade. I said before that, you know, for t smaller than or equal to 5, it turns out that the tensor powers of the set of stabilizer states span the entire symmetric subspace. Yeah, and now if we take any state psi and look at its 5th tensor power, then this is certainly symmetric. And the dimension of the symmetric subspace C2 the totally symmetric subspace over 2 dimensions and 5 copies has dimension only 6, right? And since the stabilizer powers span it, I can always write psi to the tensor 5 in terms of at most 6 stabilizer states, whereas a naive expansion would have taken 32. Yeah, and so this is an analysis which followed from our paper, and it gives the best known general bound on stabilizer rank. Yeah, so that's my second example I wanted to propose to you why you should care, because sometimes, yeah, the representation theory of these, yeah, of the Clifford group, of the symmetries, of stabilizer states, they allow you to analyze the performance of algorithms to simulate quantum computers. Yeah, and that's of course very important because, you know, if Google and IBM, they want to get money for building a quantum computer, then of course it's only interesting if they are better than what a classical machine can do. So we have to like push the classical simulation algorithms out as much as possible, yeah, so that we know at what point quantum computers have a chance only to become interesting. Good. So these were my 2 examples for why this question might be relevant. Yeah, this question. The second part I would like to explain before I state the result is, you know, I said I want to understand this representation theory, but, you know, what would qualify as an understanding I'd be happy with. All right, so let's look at this. And let's first compare the situation I'm presenting to you to a theory that's, of course, extremely well understood and very old and very important in physics and math, namely Schur-Weyl duality. So let me remind you what that is. So Schur-Weyl duality is basically the same question I asked above. It's basically my central question, except that the unitaries I have on these horizontal lines, they are not Clifford, but they are arbitrary. Yeah? So I take some unitary of C2 to the n or CD to the n. I replicate it t times, and this gives me this diagonal representation of the full unitary group. And so what can we say there? Yeah, what can we say about that representation theory? And so Schur-Weyl duality has 2 different flavors. Yeah, two different like levels of understanding, which like and the easier one is the following. So clearly there is a commuting action of ST, of the symmetric group on T symbols. Yeah, what I can do is I can just you know, I can just permute these T copies. And if I permute, yeah, if I permute these T copies, then this obviously commutes with applying the same unitary everywhere. Yeah? If I first apply the same unitary everywhere, then permute is the same as the other way around. So, so clearly these two actions commute, and the first version of Schur-Weyl duality is that they in fact generate each other's commutant. So if some operator A commutes with all u to the tensor t's, then it can be written as a linear combination of permutations and vice versa. Yeah, so that is the first statement of Schur-Weyl duality, and yeah, it describes the commutant of u to the tensor t in a linear algebraic way. There is a second, more detailed statement, namely it follows from the first, and it actually means that this tensor power Hilbert space can be decomposed jointly into irreducible and mutually inequivalent irreducible representations of the symmetric group and the unitary group. And so if you ask me now what would be a level of understanding I could hope for, then I would maybe have, yeah, first I would like to have a linear algebraic description of the commutant of all Clifford unitaries. And this we have done in this paper in 2018, and I think it's pretty much done. And I would be even happier if I could like have a reduction of these irreducible representations. And there we have some like results going in that direction, but maybe it's not yet done. It's a harder problem. Okay, right. Let me say a bit more about what makes Schur-Weyl duality so fantastic. Yeah, it has fantastic properties. And one is the following, namely, you know, if I take all these n systems here and permute them, then I can also, then this means I can permute them one by one, which means I can first, you know, permute these subsystems and then permute these subsystems and so on. Yeah, so what I'm saying here is that I started with T copies of a unitary, and I find the basis of the commutant, which is n copies of another unitary, which is a permutation. Yeah, so both algebras, the algebra generated by these U's and the commutant algebra, they are both generated by tensor powers. Yeah, so they factorize here and they factorize there. That is a remarkable property, and it is very important in applications and in quantum information that's usually called transversality. Yeah, okay, and not only do we have this transversal action here, but it's also uniform in some way, in that, you know, to get the commutant of these U's, I have to, yeah, they are generated by the permutations, which are elements in ST. It only depends on T, the number of copies. It does not depend on N. Yeah, and this will also be very important, so that we have some uniform description of the commutant not depending on N. Right, and right, and this is important in constructions, as we will see. This will often result in results which are independent of N. Good. Right. So before I state the results, there is yeah, one important, you know, related set of prior art that we should talk about, which is in North America, I believe, known as Howe duality, but I've now learned should actually be called Howe-Kashiwara-Verne duality, because Roger Howe came up with it, but he seems to have the habit of not telling anybody about his results unless you meet him in the hallway. So it hasn't, like, Howe's work wasn't actually published for many years, and before it was published, Kashiwara and Michel Verne found a very much related theory. So sometimes I have just Howe duality on my slides, but really we should, I think, remember all the people who contributed here. Okay, so now I go back to the left-hand side of my dictionary. So I go back to continuous variable Gaussian quantum mechanics, and I can ask the same question here. Yeah, so now every dot here is an L2 of R. Yeah, and I have an n-mode system here, and I can apply some canonical transformation on this n-mode system, and I can look again at T copies. Yeah. So now compared to Schur-Weyl duality, U comes from a smaller group. Schur-Weyl duality makes a statement about U being from the full unitary. So now U is a canonical transformation, so it's a subgroup. If the group gets smaller, the commutant gets bigger. So what we have acting, you know, in the commutant has to be more than just the permutations. And we can maybe hope for a simple answer, and our dream is fulfilled. Yeah, it turns out that there is an obvious supergroup of the set of permutations. A supergroup of the set of permutations on T elements is OT, the orthogonal rotations in T dimensions. And this turns out to be the right answer. Yeah, if you rotate these T modes into each other and you do the same rotation on all these n systems, again we have a transversal action, then we get exactly the commutant of the canonical transformations. Yeah, here's an example for n equal to 2 equal to n and T both equal to 2. Yeah, so here is an example of a canonical transformation, which is just the dynamics generated by a quantum harmonic oscillator, you know, which on the first system maps position and momenta into each other, rotate them into each other, and does the same on the second system. Yeah, and this commutes with like a rotation that rotates the two oscillators into each other. Yeah. And right, okay, so for the continuous variable case, the answer to our problem has long been known to Hao, Kashiwara, and Verne. Good, okay, so now we go back to our central question. I think now I've motivated why we could care and what would make me happy as a level of understanding to achieve. So let's go. Right, so here's the first result, which is the simpler result, which tells you a nice linear algebraic basis for the commutant of the Tth tensor power of Clifford group. And it's generated again by Tth tensor power. So again, we have some transversality of, and there are now two types of objects that appear, namely discrete orthogonal transformations, which I'll explain in a second, and self-orthogonal CSS code projections, which I will also explain in a second. Yeah, so let's go through these two objects that appear here and try to understand them. All right, so first, discrete orthogonal transformations. Well, let's make a simple, like naive definition again, and it's a field where naive definitions often turn out to be the right ones. So if I have a T by T matrix with integer entries, I call it orthogonal if it, you know, fulfills OTO is identity mod D. Yeah, so it's like what you would write down naively for a discrete orthogonal transformations. I will give you an example in a second. Yeah, so then this orthogonal group acts on my compound Hilbert space. Yeah, so here is again in this picture language our two-dimensional array of tensor products, and horizontally I have Clifford unitaries acting. And now I take a T by T. Okay, so now let's take a basis. Let's take an orthonormal basis for the space. And the basis is specified by choosing one basis element at every constituent Hilbert space. And so the basis is naturally labeled by a matrix. Yeah, a matrix with T rows and n columns. Yeah, and then the orthogonal group just acts on the left of this matrix, which is to say it acts independently on every column, which is this transversality condition again. Yeah, and so now, now we have this discrete notion of how to rotate these systems into each other, and it turns out that this is part of the commutant of the Clifford group. And here's one, now you all have a feeling for rotations in a real vector space, but I guess you don't really have a feeling for rotations in a discrete vector space. So here is one set of examples, which is very important for our theory. We call it the anti-permutations. And so an anti-permutation is you take a permutation matrix and then you take the binary complement. Yeah, so that is the anti-identity. You can see it it's like the identity, but it's the element-wise complement. And then over Z2, that is orthogonal. Yeah, okay, that can plug in the calculations, easy to do. And so what does it do? Yeah, if I now take this funky rotation and apply it to a state, what do I do? It suffices to understand how it works in one of these red ellipses, because again, it just acts the same way in all these, for all the other columns. Yeah, and what it does is, you see, what we're doing is we're summing up all the elements except, the diagonal one that we leave out. So we can maybe like write x bar for the sum of all the elements, but then in the ith place, we leave out the ith value. Yeah, we subtract it again. And so if we are working mod 2, then what this is this is just the parity here. Yeah, it tells you whether the number of ones is even or odd. And so what this funky anti-identity does is, in every column, it checks is the parity even, and then it does nothing, or is the parity odd, and then it flips all the bits. Yeah, and so that's one of these magic operations that turns out to be, in the commutant of all the Cliffords. Okay, I'm not doing well with time, so maybe I should speed up a bit, but I have to explain to you what a CSS code is, which is a Calderbank-Shor-Steane code. Okay, so maybe I don't. It's a type of stabilizer code. Yeah, there's a very nice early construction for how to construct stabilizer codes, and it's a stabilizer code. Yeah, and I will skip ahead. Here are examples of CSS codes. Maybe you've heard of the Tori code. Yeah, the Tori code is a CSS code, but I will skip this detail for now. And I will return to the first result. Yeah, so the commutant of the Clifford tensor powers is generated by, again, tensor powers of finite orthogonal transformations and also self-orthogonal CSS code projections. Yeah, so I choose one of these objects, I tensor it up t times, and that gives me a basis for the commutant. So the good news is it's again transversal, which will be very important. It's again uniform in that it doesn't depend on n, this description. Yeah, but these factorizing generators, they are not quite a group, because sometimes we have these code projections. And this makes the theory a bit more complicated, but also very interesting. And I won't have time to talk about it, but if you ask me, I can tell you a bit later. All right, back to applications. Now that we know, now I go back to this guess whether Gauss example. Right, so the first corollary of all this is that stabilizer states have an additional symmetry. And let me explain what I mean by this. So now I consider a stabilizer state on n qubits, and next I consider its tth tensor power. So before, on these horizontal axis, I had unitaries. Now I put states there. Yeah, I take a state, tth copies of it. Then it follows that tensor powers of stabilizer states, that these kind of objects I get, they are invariant under the orthogonal group, under this discrete orthogonal group. Not just, so unitaries, tth tensor powers of unitaries commute with orthogonals, and the states, they are left invariant. And the proof is 3 lines, but I'm again a bit behind time, so I will leave it here, and then again you can ask me if you want to see it again. It's very easy to see. And now I can I return to the question that I raised but didn't answer before, namely I can give you the answer to the guess whether Gauss question. Right, so somebody chooses a state on n qubits, and they give you 6 copies. And now you do the following thing. Yeah, you measure the projection onto the +1 eigenspace of the anti-identity. So the anti-identity, again, is this funky orthogonal thing. Yeah, and we know that if people gave us stabilizer states, then they lie in the +1 eigenspace. Yeah, so stabilizer states will always be accepted under this test. Yeah, if I get this +1 eigenspace projection. Yeah, and the alternate outcome, namely the -1 eigenspace, or the eigenspace is orthogonal to the +1 eigenspace. Yeah, if we measure those, then we say it's not a stabilizer state. And this works, yeah, if psi is a stabilizer, then by what I've told you before, this protocol will accept with probability 1. And it also turns out that if psi is far away from the set of stabilizer states in that the maximal overlap with any stabilizer is bounded away from 1, then the acceptance probability will also go down. And that's in fact the optimal behavior that you can have. And so now we've solved this open problem in quantum property testing that I said before. Yeah, so with 1 to 5 copies, it doesn't work, but with 6 copies, it does work. Yeah, and so the important takeaway is not that 6 is an important constant of nature, but that it is independent of n. You know, n can be very large. So these states are living on a gigantic Hilbert space. So there is no way that you can classically, you know, get full information about them. Yeah, but this quantum algorithm here can identify stabilizerness in an effort that scales independently of n. Right. Good. So now I don't have much time. It's a 1-hour talk, no? I don't have what, is that true? Arthur, maybe you can guide me, because now I can come, here's a natural breakpoint, but I can come.
Go a few minutes over.
Sorry?
Go a few minutes over, and then we'll have a discussion.
Oh, I'm already over time. Is that true? Okay, so I thought it...
You have 5 minutes to an hour.
Okay, 5 minutes. 5 minutes. Oh, that's fine. Okay, 5 minutes. So now I can tell you about the application that actually I wanted to hear about, namely quantum homeopathy. So what is that? Right, so this an old question is about the convergence of a random walk on a group. Yeah, if you take some group G and some set of generators, then you can ask how big does M have to be such that the distribution of a random word, GI1 to GIM, with respect to these generators, approximates the Haar measure on the group. Yeah, it's a very general question. It depends on the group, it depends on the generator, it depends on your notion of approximation, but many instances are known. So there's one famous example due to Percy Diaconus, who said that, who proved that, you know, if you want to shuffle 52 cards, then you know you need 7 basic shuffles. They are necessary and sufficient to randomize the deck of cards. Yeah. And now what we want to do is we want to understand quantum shuffling. Yeah, so it's a particular instance of this random walk idea, namely, yeah, you take n qubits and you take a set of quantum gates, G1 to GK, and you ask how big does M have to be such that the distribution of a random circuit approximates the Haar measure on U to the 2 to the n, U of 2 to the n. Yeah, so that is the quantum shuffling question. This has many applications. There are exciting applications like the black hole information paradox, but I don't understand this, so I will not talk about them. And then there are boring applications like in quantum encryption, which I do understand, so I will briefly mention that. Okay, so let's say in quantum, here's why we care about these random walks. Let's say that Bob has a state and wants to transfer this state to Alice. Yeah, but there is an eavesdropper in the middle and they don't want the eavesdropper to get any information. So what they can do is they can like agree on a secret key, which is a classical key. Yeah, and it's just it's just a random word. Yeah, it's just like a sequence of generators. And so they translate this into a quantum circuit and they use this quantum circuit to scramble the plain row. And then they get like an encoded cipher. Yeah, and so they want the cipher to really have no information about the plain state if we don't know the key. Yeah, so that is a simple cryptographic protocol. And what you need for this to work is we need a short key so that, you know, it's efficient. But also we need an easy fault-tolerant implementation. So these gates here should be like easy to do on a quantum computer. Ideally Clifford-based. No, I said before, Cliffords are the one we can do fault-tolerantly. Right, okay, so let's see whether we can do it. Right, so that's why we want to do it. Next question is, what is the notion of closeness? How do we measure approximation to Haar? Yeah, and so here's a definition. We call a distribution U on the set on the unitary group a T design if the following is true. Yeah, if integrating over that measure and applying U to the tensor T to an input is the same as integrating over the full Haar measure. Yeah, and that should be the same for every input row. And if a measure nu has this property, then we say it approximates Haar measure up to tth moments. Yeah, so that's the definition of a unitary T design. And for some cryptographic applications, one doesn't need too high T. Yeah, and then we can also epsilonify it. So here we have equality. You know, maybe often it's okay to relax it a bit, but I will not talk about that. So there were some prior results on this randomization procedure, namely like the diagonal result. Yeah, it's quite badly in T. But what is worse is if one restricts to Cliffords, then one can only reach T equal to 3. Yeah? Because a Clifford group, it's a group, there's a group theoretic obstruction to going higher. Right. And now here's our quantum homeopathy result. It says that if you want to have the scrambling effect, then order T to the 4th non-Clifford gates are sufficient. And so the important thing is that this does not depend on n. It will randomize information for an arbitrary number of qubits using a number of non-Clifford gates that does not scale with the number of qubits. Yeah, so the density of non-Clifford gates goes to 0 as n grows, and that's why it's called homeopathic, you see? Right, and that is the main result there. And yeah, I don't have time to really talk about the proof. I've seen Bruno Nachtergaele before in the list of participants. It uses some theory by him, and it's really a bit painful, but there's ideas for making it better. But yeah, I will not talk about them. So here's the summary of our quantum information results. So we have found the commutant of tensor powers of the Clifford group. They are generated by orthogonal transformations and CSS codes, and there's many applications. And then I have another entire deck of slides about representation theory, but I have no time, so I will just go through it to go to my goodbye slide. That's all stuff you didn't hear. Nice pictures, no? And thank you. There we are.
Well, thank you very much, David, for covering a tremendous amount of interesting material. And I think maybe if we ask for questions, it's good to unshare the screen so we can see who's talking. Are there questions?
Yeah, so I missed that stochastic orthogonal matrix.
Ah, yeah.
How is it?
That's right, the word stochastic here. And this is completely my fault because I took it off my slides almost everywhere, but not quite everywhere. And it relates to my universal disclaimer I had in the very beginning that everything I say, where's my universal disclaimer? Oh, you can't see my slides, no? Okay, so I try, okay, I was like flipping through my deck of slides, but forgetting that you can't see it. So my universal disclaimer was that everything I say is true, but in characteristic 2, you have some additional properties. And in characteristic 2, orthogonal is not enough. You also have to have the additional property that O applied to the all ones vector is again the all ones vector. And that we call stochastic, you know, because it's like, yeah, it's something that permutations, for example, do and convex combinations of permutations. And our anti-identity does it. It is 6 by 6, and it has an odd number of ones in every row because there's 1, 0. And so applying it to the all ones vector will give you again the all ones vector. So that's what the stochastic means. It's maybe not a very good name because it has nothing actually to do with, you know, a stochastic process or something, just by analogy.
Yeah, no randomness, okay.
There's no randomness, yeah, exactly. No, it is just a formal analogy, maybe not a very good term.
Thanks.
Thank you, Rad. Are there other questions?
I have a quick question.
Who's speaking?
This is Ambar Sengupta. I'm trying to you made a statement that all Gaussians arise this way.
Yeah.
Yeah. What was the significance of that?
Right. Okay. So the so by all Gaussians arise this way, I mean via the stabilizer construction. Yeah. So let me again say what this way means. So this way means you take an isotropic space of a finite symplectic vector space. You go to the Weyl operators corresponding to that. and you look at their common +1 eigenvector. Yeah, and then every one of these discrete Gaussians, yeah, where you take, you know, a d-root of unity and put a quadratic dependency into the exponent, yeah, for any one of these, you can find an isotropic space that will reproduce them. But in fact, there's a few more, and I didn't say it in my slides, but I can tell you now what are, you know, the additional wave functions that are stabilizer states that are not directly Gaussians, and they are exactly obtained the following way. So you view your Hilbert space as L2 functions on ZD to the n, so as L2 functions on a discrete configuration space. Then you take an affine subspace of ZD to the n, and you restrict a Gaussian onto this affine subspace and set it to 0 else. Yeah, so it's a kind of like compactification, if you want, yeah, where wave functions with non-maximal support and with support restricted to an affine space also enter. Yeah, these are of course not Gaussians because Gaussians have full support. Yeah, that's why I use this indirect formulation. Mm-hmm.
Thank you.
So does your guess whether Gauss result, which you stated for qubits, hold for qubits?
Yeah, so everything I say holds for both qubits and qubits, but for qubits, it's always a bit, there's minor differences. Yeah, it's again, my universal disclaimer is that I don't like put on every slide like the variation that you have to apply to get the characteristic truth thing to work. So everything I do works for in any characteristic, but you know, there's always some minor technicalities to take into account. Yeah.
So Schur-Weyl, you're an expert on Schur-Weyl duality. Do you have any comments?
Oh, we have an expert in the audience, so that is
I'm not
very exciting.
Well, first, it's very interesting to know the Schur-Weyl duality for Clifford groups. And one thing I'm...
turn on your video.
Okay.
Hey.
Okay. And one thing actually I discussed with David, I think last year at Switzerland. And one thing would be interesting is in our QAnon language, we have the picture representation of the Clifford gates.
Yeah.
And then it would be natural to understand the representations also in a pictorial way. And then the question is whether we can find somehow a canonical basis for the representations of the tensor power of Clifford group in terms of pictures. I think that's possible. Namely, the basis of the irreducible representations are given by certain pictures. And if the vectors in the same irreducible representations could be some equivalence of the pictures, pictorial states. And that may give a like pictorial construction of the irreducible representations of the tensor power of the Clifford group, which may be also useful to study like you mentioned the Clifford stabilized rank of the tensor of T gates, T states. Since essentially T states is also has a pictorial representation, but it has linear sum. And then the question is whether we can minimize the number of components in the sum using stabilized states, and often can be somehow understood in a pictorial way. But this doesn't give the answer directly, but I think it's interesting to study it in this way.
Yeah, I think these are both like, I'm wildly interested in the answer to what you proposed, whether this program could be made to work. This would be just super fantastic. I don't know how to do it, but yeah, so yeah, partly referred to the part of the talk I didn't even touch upon, namely, like these irreps that appear this way, can we describe them in a nice way? And so currently we can't. Yeah, and yeah, if there's any way of doing it, pictorial or not, it would be fantastic. But if it's pictorial, of course, it would be super fantastic. Yeah, but I continue to have no idea how to do that. Yeah, but yeah, so I think we should definitely, if you're optimistic, we should definitely continue the discussion. Yeah.
So are there other questions?
Yeah, okay. I have a question.
Alina.
Yeah.
Yeah, so it's not quite related to your talk now, but it's just a while ago you had a series of papers like about quantum expanders, and did it find some applications like in quantum information theory, and what was the development of this subject?
Oh, it's a good question. It's a series of papers really assumes an honor I don't deserve, because there was one paper from my point of view, and it's a bit related because it also used some kind of Clifford construction.
Yeah, that's why I ask, right? That it's not completely out of the way.
Yeah, no, it's good. And yeah, they did find applications, though I think this has died down a bit. There was, there was a quantum many-body a question that people cared about a lot back in the day, and expanders provided like a counterexample to that. And the question is whether, you know, in a spin model, a clustering of correlations. So if correlation functions like decrease very quickly, whether you can use this to make any statements about efficient representations of these states, whether all states that have, that show clustering have a certain efficient representation. And this turned out to be wrong. Yeah, and quantum expanders provided the counterexample. But the reason we cared about like states with clustering correlations is because, you know, ground states often have this property. And a bit later, Matthew Hastings managed to prove that ground states, which people were actually interested in, have such an efficient representation, not using this clustering of correlation. So yeah, so these expanders, these quantum expanders, they had a bit of a short time in the limelight, you know, because there was one approach to a very important problem, and they showed this approach doesn't work, but maybe a year later another approach came around due to Matt Hastings, and the statement people actually were interested in was then established. So ever since then, I think it's a bit, you know, it's gone a bit quiet in this field, or maybe I want to stop like reading up on the subject. So yeah. So they had that time, but I'm not sure. Yeah, I'm not sure how up to date that field is, or what current applications would be.
Yeah, thank you very much. It just maybe not exactly quantum expanders, but what I had in mind, it's some kind of more higher dimensional constructions in this period. But what you're absolutely right that this kind of connection with Hastings, he also gave a talk in this seminar some time ago. Yeah, so this is like what I'm thinking, kind of higher dimension analogies of what he was thinking.
I mean, in a way, like this homeopathy result is, of course, like if you want to interpret your question very generously, also goes into that direction, namely, so this expander property is a particular randomization property. It means in a particular sense, they are good randomizers. Yeah, even though you have a small set of unitaries, which are good randomizers. So our designs also capture this idea of quick, like fast randomization using little randomness also. Yeah, if you want to have a small key size, a small set of unitaries that like scramble state space efficiently. Yeah, and so in this sense, you know, it's a kind of a continuation of this old question. Yeah, to which extent can you use maybe these phase space-based techniques to find good randomizers which require, you know, few elements. Yeah, but it's a different notion of randomization. It's on a technical level, it's different notion of randomization. Now we use this T-design property, which seems to be better suited to these applications, different from what these expanders did. Also, the expanders that we constructed in our old paper, they were just Cliffords. And so in our, so with respect to this design notion, they couldn't be very good.
Yeah, thank you very much. No, it's more like philosophical question.
Yeah, it's a good, I know, but I agree with you. It's all, it's all connected. Yeah.
Thank you very much.
Thanks.
Are there other questions? Well, if there are no more questions, then I'd like to thank David again. It was really a beautiful talk, and unmute yourself.
Yep, thank you for the invitation.
Bye-bye. See you next week.
All right. Bye. Thanks for your attention.